thanks so much for clicking onto this video. We're going to be learning about bond enthalpies today, so here are the learning objectives. We're going to define the term mean bond enthalpy, and then we'll be using these mean bond enthalpies to calculate approximate values for the enthalpy change for reactions in the gas phase. And we're also going to explain why values from mean bond enthalpy calculations differ from those determined using Hess's law. We're firstly going to define what mean bond enthalpy means. And basically, this is the mean enthalpy change to break 1 mole of covalent bonds in the gas phase. So it's really important to remember that it's in the gas phase, and also it's 1 mole. And because it's the mean, we've averaged it from bonds in different compounds. So in different compounds, you might get OH bonds. So OH bonds can be found in alcohols, but they can also be found in molecules such as water. And we average all of these same bonds to get the mean bond enthalpy. Now we're going to discuss how to work out the enthalpy change from the bond enthalpies. So we're going to use this example of hydrazine, which is N2H4, and it's used as rocket fuels. So this is the equation when it burns. We need to calculate the nitrogen-nitrogen bond enthalpy in hydrazine given the following bond enthalpies. And first of all, what I like to do is to draw out the molecules because it's quite hard to visualize them sometimes. So N2H4 looks like this. This is N2H4. And then for oxygen, we have O double bond O. And then for nitrogen, we have a triple bond. And for water, we have H2O and another H2O. So now we've drawn them out, we can clearly see how many bonds we need to break, and it'll help us when we actually get on to calculating all the numbers. So I'm just going to write out this equation. And then what we do is we just write out the atoms, because if we break all the bonds, we'll end up just with separate atoms. So this bit's quite easy. The N2 will become 2 nitrogen atoms, and these will all be gases because the definition is that it's in gas phase when we look at bond enthalpies. And then we've got 4 hydrogens, so we just have 4 H's, so 4 H atoms, which are all gases, and then also 2 oxygen atoms. And if we go from this to this, then that is the enthalpy, the bond enthalpy for the N2H4 and oxygen. So now we look at the molecules and think, how many bonds am I breaking? So each NH bond requires 388 kilojoules per mole of energy. And when we break bonds, energy needs to be put in, so they're all positive. And so we have 1, 2, 3, 4. So we have 4 times 388. And then we have 1 double bond oxygen, so 498. And that gives a total of 2050 kilojoules per mole. But then we need to remember that we've still got this bond here, and this is what we're trying to find. This is the NN bond that we're trying to find. So we need to add an X onto here, and that's an unknown value. And then with this, it's the same. So if we go from nitrogen to 2 nitrogen atoms, that's going to be the bond enthalpy again. So we use this bond, which is nitrogen 44. and then we add on what the two waters are. So we've got 1, 2, 3, 4 OH bonds in total. So we add on 4 times 463, and that comes to a total of plus 2796 kilojoules per mole. And this is minus 583, as it says in the question. So now we can find what X is using Hess's law. So that means that we can start here and we can finish here. And then we have that minus 583 plus 2796 is equal to, if we just go from here to here, so that'll be X plus 2050. And now we rearrange for X. So X equals 163 kilojoules. And this is the bond enthalpy of the NN bond. This should always come out as positive because breaking bonds requires energy. So if you do have a negative figure here, then you might have gone wrong somewhere else. So in this example, we ended up working out a bond enthalpy, but if we did want to work out the enthalpy change, we would do the same thing, but we would have been given X instead of this minus 583, and you would have done the same thing with the Hess's law to find out what this would be instead. A very important detail that you need to remember is that values that we've calculated from mean bond enthalpy calculations differ from those which we've determined using enthalpy change of combustion or formation using Hess's law, and that's because the mean bond enthalpy is just the mean, so just the average of the bond enthalpies of covalent bonds in different compounds, so it's not very accurate. So before I move on to the question, feel free to pause the video and try it yourself first. So find enthalpy change for the following reaction using the bond enthalpy data below. First, I like to start off by writing out the equation. So we have C2H6, and that's a gas, plus 3.5 oxygens, and then we think about the bond enthalpy. And what does that mean? Well, basically we're breaking all the covalent bonds, so we form just the ions by themselves. So this carbon 2 would form 2 carbons, and they would be in their gas state because that's how bond enthalpy is measured. They measure it whilst everything is gaseous. And then this hydrogen 6 would form 6 hydrogen atoms, and then this would form 7 oxygen atoms. So these two would give the bond enthalpies. And now I like to draw out the molecules. So we've got C2H6 here. And we have 3.5 oxygen double bonds. So we've got 1, 2, 3.5. And then we've got 2 carbon dioxides. So we've got 1, 2, and then we've got 3 waters. So we've got 1, 2, and 3. You might not necessarily need to draw these out after a while, but it always helps to have them on the side, just in case you can't visualize how many bonds there are. So here for C2H6, we're first going to look at the CH bonds and to see how many we need to break. So we have 1, 2, 3, 4, 5, 6. So we're breaking 6 of the CH bonds. So it'd be 6 times 412. And then we have a look at this bond here, and this is a carbon-carbon bond. So we add on 348. And then we also add on these ones here. So there's 3.5 of these 496 oxygen double bonds. So we add on 3.5 times by 496. And that comes out to be plus 4556 kilojoules per mole. Then we do the same for the other side. So we have 4 of these carbon double bond oxygen bonds. So we have 4 times 743, and then we add it with these 6 OH bonds. So 6 times 463, and then we add these two together, and we get plus 5750 kilojoules per mole. And now we think about Hess's law again, and we think about how any way we go about the reaction from reactants to products, the enthalpy change should be the same. So say we started here and finished here, then the enthalpy change from this starting point this way should be the same as just going directly like this. So then we can form an equation. So this is the delta H that we're trying to find. So that means that we have delta H plus 5750 is equal to 4556. And rearranging gives that the delta H is minus 1194 kilojoules per mole. And because there's a minus sign, we can actually check to see if it's right, because if we look at this equation, this is actually an enthalpy of combustion, and we know that combustion is an exothermic reaction. So this should actually turn out as a negative figure. So we know that it could be right. Hi everyone, thanks so much for joining me for this lesson. Today we're going to be looking at a harder question for the topic of bond enthalpy. So you can click off the video and try it yourself first, or just follow along as to what I'm doing. So it asks us to calculate the enthalpy change of formation of CCl4 given the following data. And the first thing I'm going to do is to write out the equation for the formation of CCl4. So the enthalpy change of formation measures the enthalpy change when 1 mole of CCl4 is formed from its constituent elements when they're all in their standard states. So that means that we have carbon as a solid added with chlorine, and it exists as a diatomic molecule, so chlorine as a gas, and then that forms 1 molecule of CCl4, which is a liquid. And so now I need to balance it. So we've got 1 carbon and then 4 chlorines on this side, so that means we need another chlorine molecule on the left-hand side. And this should be the delta H of formation. And now what we do is we have a look at the equations and see what we can kind of get from it. So bond enthalpies, we know the equations for those. So for the Cl-Cl bond, it would be if you broke down a Cl2 from gas to 2 Cl atoms, which are also gaseous, and then the bond enthalpy for this probably will help us with the carbon tetrachloride. So now you kind of have these things in mind, we can kind of set up an idea of what we want to do. So if I put this at the top, I've got the carbon, which is a solid, plus with 2 chlorines, which is a gas. And then this is the delta H of formation. And we form the carbon chloride, the carbon tetrachloride. And so now the next thing we have is that a carbon solid gets turned into carbon gas. So here, if we turn the carbon solid into a carbon gas, we know that this is 715 kilojoules per mole. So we can go ahead and do that. So this is going to get turned into a gas, and we're still going to have the 2 chlorines as a gas. And then for this bit here, we see that we're given the carbon tetrachloride to gas. So we can do the same thing here. And we know both of these. And then we think, oh, but if we use this, we can actually get the bond enthalpies, because these are both in their gas forms, and so is this one. So then we just get the separate atoms. So we get a carbon atom and 4 chlorine atoms, which are both gases as well. And we see that these are both given to us as well. So this is our diagram. And so now we add in the numbers. So here we have plus 715. And then here we have plus 31 kilojoules per mole. That should be kilojoules per mole as well. And then here we can now draw the molecules. So you've got CCl4. So you've got C with 4 chlorines attached. So that means that we're breaking 4 CCl bonds here, plus 338. So that would be 4 times 338, which equals plus 1352 kilojoules per mole. And then here, the carbon doesn't do anything because it stays as a carbon gas. But this chlorine here, the covalent bonds are broken and it becomes 4 chlorine atoms. So 2 chlorines look like this. So you've got 1 chlorine and a second chlorine. And that means that we have 2 of these chlorine-chlorine bonds. So we do 2 times 242, and that equals plus 484 kilojoules per mole. And now we should be able to work out this delta H of formation, because when we remember Hess's law, it states that from reactants to products, any route you take, the enthalpy change will always be the same. And so if we call this the start and this the finish, that means that if we go this way round, we'll get the same enthalpy change as if we go this way round. And so now we can set up an equation. So we have 715 plus 484 has to equal the delta HF plus 31 plus 1352. So rearranging this gives us that the enthalpy change of formation of the carbon tetrachloride is equal to minus 184 kilojoules per mole. And we can check if this is kind of right, because the rule is that when we form bonds, the reaction is exothermic, so heat is lost, heat is transferred to the surroundings, so this should always be negative.